Welcome back, welcome back, welcome back. I'm Lisa Blackburn. I'm doing this weird. And this is my YouTube channel where we talk about everything I want to, science and math. And this is chemistry class. And we're going to be talking about reactions. And I'm moving this around. This makes for great TV. My finger in it. Okay, there you can see the screen. All right, guys, let's get started. So you got your new notes. We're going to finally start getting to do some real chemical reactions. Yay! So we're going to do several labs. We're going to start with the microscale lab, where we're using more dangerous chemicals, but in a small amount, so it's less dangerous. And then we're going to build up to a macroscale lab, which will be our most chemically lab that we've done so far, and we'll get to learn a lot of techniques. Now, I had a question also about our water lab, and we are still working on doing that. But I was sort of waiting to hear back as to see if we could use the drone, because it would be more fun if we could use the drone. But if not, we might. If I don't hear back from our drone instructor soon, we might go ahead and do the creek part and then do the drone in a separate one. But it'd be fun if we could do it. But he has not written me back. I don't want to harass him.
I'll talk to him first.
Yeah, talk to him. Say, when are we going to be able to do that? All right, so let's talk about chemical reactions. Okay, so what is a chemical reaction? A chemical reaction is a chemical change. And what's the abbreviation for change that we use? A triangle, the Greek letter delta. Take that off of there, go back there. All right, and it's one or more substances being changed into something new. So if I take water and I boil it, and it becomes water vapor, has a chemical change taken place? No, it's still H2O. It's gas H2O, but it's still the same compound. For it to be a chemical change, it is going to have a new compound. And we're going to break bonds and reform bonds and make something new. So one of the things we'll do with physical science, I do it as a pop quiz. I don't know if we're going to take the time for you guys, but you have to go through and say, is this a physical change or a chemical change? So a chemical property or a physical property. But y'all might have a pop quiz on that. Now, y'all supposedly have learned this before when you had physical science in 8th grade. What is the original substance called? The reactants, yes. And what's the new substance called? Products. Sounds like you're making something at a factory. Products. Now, the evidence a chemical change may have occurred. Sometimes it's hard to tell. Sometimes it's hard to tell if a chemical change has happened or not. All right, so I'm going to do a chemical reaction for you. I know it's an exciting chemical reaction. All right, so when I do this chemical reaction, tell me what evidence of chemical change we have going on. Okay, what do we have?
Fire.
Explain, well, how do you know it's fire? Heat and light. Color, there's a color change. It was green and brown, and now I have black and a fire that's yellow and blue. What else? Max might could tell, or Jeffrey. Listen. Do you hear the little crackles at the front and the back? Y'all probably can't hear it, but we have some sound given off. What else? Smoke. And in particular, if you're looking at smoke, you should always tell the color. What color was the smoke? Can you see it? It's kind of white, gray being given off. Anything else? Can you smell it? Smell the burning? So we have a smell there too. Now, could I get my original match back again? No. So this is a reaction that went to completion, not completely because I still have some stuff here, but it is something you're not going to be able to get your original thing back easily. when we talked about boiling water into vapor, I can get that water back again, can't I? I can condense it. That's how stills work. You boil them, you condense the vapor back again. Is how you do that. Okay, so let's write some of these down. The first thing we all said was we had heat. And in particular, it's a change of heat. It could be cold. It could be not just giving off heat. You know those ice packs, you break them and shake them and then put it on your injury. Does anybody ever seen those? We'd like playing the sport. I used to coach boys baseball. I know. You wouldn't guess it, would you? But one of my jobs as assistant coach, I wasn't head coach, was I was in charge of the first aid kit, and we would go through those ice packs. We would use 2 or 3 a practice. Those boys loved having some sort of injury and getting one of those ice packs on it. So, yeah, we were high users of the ice pack. Okay, so I coached like how old were those kids? They were like 9, 10. They weren't, well, then I moved up and I did the high schoolers. All right, so change of heat. Another one, the second one y'all said was light. It gave off light. It also made a noise. We could hear our crackling little fire. We had a color change. We had a change in color. Now, all 3 of these, the heat, the light, and the noise, are all a change with energy. So remember, big E is the symbol for energy. We also had smoke given off, so we had production of a gas. And then you can also have production of a solid. And you call it, when you mix 2 liquids together and you get a solid powder in it, it's called a precipitate. And the symbol for it is PPT, or an arrow down. So a lot of times you have 2 test tubes, you mix them together, and you get a solid to form in it. Let me see when I'm going to do that. I could go ahead and show that. Okay, so I brought one to show you, an example of that. Okay, so here I have 2 chemicals. I have sodium carbonate and calcium chloride. I'll show for those at home. They are both clear liquids. This one, the calcium chloride, has a few little bubbles in it. The sodium carbonate does not. Okay, and I am going... We have some loudness going on. I'm going to mix them together, I think, in here. There we go. All right, so I'm going to mix these 2. I'm going to start with the calcium chloride. Let's see, probably that should be enough. Okay, and I'm going to pour into it the sodium carbonate. Woo. See how it got cloudy? Also notice that the cloud is suspended throughout. Now, if we let it sit, it would eventually come out. This little experiment is called cloud in a bottle. Does it kind of look like there's a cloud there? I'll hold it up here so that they can see it. And I'll walk around so y'all can see it.
This Blackburn looks like the tap water at our school.
It does. The tap water at our school is a little alerting. I was distilling it, so there was leftover stuff in the still, and it was kind of gross what was left over. I was surprised there was anything left over, except maybe some ions, but there was like this green sludge stuff left over. So this is our solid precipitate. Cloud in a bottle. We have a bottled cloud. It's kind of romantic sounding, but that's what it is. All right, so there's our little demonstration of that one. I didn't use too much lab safety with that. Y'all noticed? One of the reasons is these are not very very dangerous chemicals at all. And in fact, the sodium carbonate is some stuff you use with detergent. A lot of times you add this to your washing machine to make your clothes get cleaner. You don't normally wear goggles when you wash your clothes, so this was not very dangerous. So I didn't worry too much about the safety equipment with that one. Just to let you know that I'm not really being slack on the safety. All right. So now another point of this is chemical reactions release or absorb energy. Big E is energy. They can either give off energy like our match, or they can take in energy like those cold packs I told you about. So which one do you think is giving off energy? Endothermic or exothermic? Exo, because it sounds like exit. Sounds like you're leaving, right? So endo is taking the energy in, endo. So endothermic takes in energy. And an example would be the electrolysis of water. I'm going to just put cold packs. I think the other one's kind of confusing because we're not really going to do it. Cold packs is an example. Exothermic gives off energy. And an example for that would be hot hands. Have you ever gotten the ones where you break something and it gets hot? They sell them as an impulse item in the winter. Now, fun exothermic facts. The more stable, once it gives off the heat, it's more stable. So that's why it reacts and why it gives off the heat. The stronger the bond, the more energy that is released. And also, the great majority of reactions are exothermic. The great majority of reactions are exothermic. Now, atoms are rearranged in the chemical change, and that's what I was telling you before. You have to make something new, and they must obey the law of conservation of mass and energy. What is the law of conservation of mass and energy?
You can't either destroy or create.
Right, you cannot create or destroy atoms or energy. There was a point of creation, because there's stuff here, so it must have come from somewhere. But since then, since that point of creation, atoms cannot be created or destroyed. They just change from one form to another. So the atoms that make you up have been here since day one of creation, ever since everything started. And we have different theories about that. And it's debated because, it's the past and we don't have a time machine and we can't go see it. But we know that there's, ever since then, that these atoms have been around. They're not new. And the same thing, weirdly, with energy. Energy cannot be created or destroyed. It only changes form from one to another. And that's the hard one. The atoms make sense to me, but the energy is harder for me to get my head around. So you must obey the law of conservation, and it's that matter, or atoms, matter and energy cannot be created or destroyed. They can only change forms. Good so far?
Yep.
Then I'm going to scroll up. Ah, pooey.
You're still in draw mode.
Okay, take it off. Just go home.
Oh.
Oh.
No, you've selected the drawings. Like, click on the page for that. Scroll now.
It's at home now. Still, I might have to close it out.
You might want to save it. Was it off? It's automatic.
I don't care. It doesn't matter. Let's see. I don't care if the writing's on there.
I have no clue what just happened.
It didn't used to do this, but it does now. So I took all the drawings off to try to make it better. Okay. How are reactions written? accurate. We want to have accurate chemical reactions, and they are like a recipe for chemical products. Now, I used to do this. So this is a recipe. It was invented by my next door neighbor, Mabel Johnson. Mabel Johnson won the Pillsbury Bake Off. She got $100,000 and a new kitchen. This was not the recipe she won with, however. It was one of the ones she made up. Yes? Oh, yeah, they must collide. I must have scrolled too fast. Let's just do this and we'll go back, okay? Since we got it, do this. Let's do this little part and then we'll go back, okay? So jump down to it's a recipe. Anyway, so Mabel made up this recipe, and it wasn't her recipe that won the Pillsbury Bake Off. The recipe that won was a onion cookie that you have with soup. But she won $100,000 in a new kitchen. But anyway, she made up this recipe, and it is extremely popular now. And it's for peanut butter cookies. And I wrote it like you write chemical reactions. Normally you write recipes, you list all the ingredients, and then you write underneath what you did. But a chemical reaction is a recipe that tells you the same information, but it's just written differently, and this is how you write it. The things on this side of the arrow is what goes in it. The amounts are the numbers written in front of whatever you're putting in. So my recipe is 1 cup peanut butter, PB, that's short for peanut butter, not lead. 1 cup sugar, 1 egg, and 1 teaspoon vanilla. You mix that up and you cook it, and it makes, what it yields is 1 batch of peanut butter cookies. What does this not have that most cookie recipes have? Flour. So all these people out there that are gluten-free, who can't have gluten, they love this recipe because they can have cookies, and all these people who can't have flour, because it uses the protein in the egg and the peanut butter, so it doesn't have to have flour. So what I used to do is I would let my chemistry kids, to replace their lowest grade on a test, they could bring a batch of cookies. They would have to make the cookies. They would have to think about how it's a recipe. Cooking is chemistry. Think about this. We're breaking and reforming bonds. Could we get our egg, sugar, peanut butter, and vanilla back out of the cookies once we cook them? No, we have broken bonds and we have reformed bonds. It is chemistry. So this take-home lab, it's a chemical lab you could do at home. I would let the kids do it, and then they would bring their cookies on a day, and we would all eat them, and it was real fun. But now there are so many kids with peanut allergies, I don't think I could do it. I'd be killing kids.
You do it with brownies.
With brownies?
I love brownies.
It's not as good though. So anyway, what I did last semester is I let people do the cookie assignment if they wanted to for a digital learning, and they had to take pictures of themselves with their pan of cookies in their kitchen with, them and their cookies. So I knew they did it and not their mom, that I knew that they did it and they didn't buy them at a bakery. And then they had to bring me 3 cookies in a Ziploc bag to school so I could tell they were really homemade and not store-bought. And also, for kids who have peanut allergies, I let them do a different recipe, but they had to write it. They had to figure out how to write it in chemical form. Do y'all want that?
Yes.
That? Okay, we'll do it. No, I don't want you cooking them on Friday, because then they wouldn't be very tasty when you brought them to me on Monday. All right. So we'll have our little makeup lab, because some of y'all desperately need something to take care of that bond test, don't you? Yep. This is right up your alley, right? Chemistry applied. All right. So now let me go back and see what I skipped.
You skip
Particles must collide. That's what
3 and 4.
I missed skip 3 and 4. Let's see if we can do it. I know. I'm going to erase this. I did.
That's right. She wasn't there.
Yep. I skipped 4. All right, go back here. Okay, for a reaction to happen, the atoms have to touch. They have to come in contact with each other, so they must collide. Come on, you can write. Y'all are getting excited about your cookies. They must collide for a chemical reaction to occur. And for example, this reaction. The reaction I did, I made the chemicals here collide with the chemicals here. Do you think my match will light if I just hold it here? No. Will it work if I just hold it here? Maybe if it was hot enough or, given enough time. But I have to really smush these chemicals together, and then I can get it to react and get the reaction. They used to have strike anywhere matches where they put both chemicals in the match head and you could rub it on like concrete. There are videos of guys rubbing it on their rough beard and then striking a match on their face. So it was, or on the bottom of their shoe, on the boot, and they could light it. You don't see those so much anymore, because what would happen is people would leave them in their car and they would have them on the dash and it would get hot. And it would give enough energy for that reaction to start, and they'd catch on fire and burn up people's cars. So, yeah, you shouldn't leave matches in your car. All right, so for example, was our match. Y'all are so excited today. The match reaction is potassium chlorate, and the other part of it is phosphorus. And it yields potassium chloride plus phosphorus 4 oxide plus energy. So that's the reaction that's going on in our match. All right. So now let's see if he'll let me scroll again. I'll go over here. See if he'll let me scroll up. Okay. So now go back underneath the recipe. In the chemical reaction, what we're going to be learning about a lot on this one is this chemical reaction. Atoms and masses are conserved.
Before the interruption, at this time we need Braden Beal to report to the front office. Braden Beal, report to the front office.
Yes? Hold on, I can't hear you. What? I think they are doing a lab out there. I don't think they even.
No, he's trying to give you something.
Then go get it. Go open the door and get it. If it's for you.
No, I think it's for you.
It's for me. Oh, maybe he wants to give me food.
Oh yeah.
Would you like a donut?
Yes, I'd like a donut. What kind are they? They're all the same?
Yeah, they're all
Is that more than one flavor?
Just wrote in the door.
Thank you so much.
Have a great day.
I got a donut because I'm a member of DECA. See my shirt, so donuts for DECA. I got a very pretty white donut. Okay. You probably could have taken that and I wouldn't have known since we thought it was for you.
Oh yeah.
All right, coefficients indicate the amounts. My pen is not writing good. All right, so what this is talking about, in my recipe, the amounts are the big numbers in front. It's 1 cup peanut butter, 1 cup sugar, 1 egg, 1 teaspoon vanilla. So anybody ever made these cookies, my Mabel Johnson cookies before? See, it's gotten real famous because of it was published. When she entered that one, she didn't win, but she made the book. So it was published a long time ago in a pills. They do a little cookbook, like a magazine you buy in the grocery store of the finalist recipes and the winners. So that recipe got published as a finalist the year she didn't win, and that's why it's out there and everybody knows it now. Okay, the next idea is that reactions must be balanced because of the law of conservation. What you put in is what you get out. So here I have hydrogen gas plus oxygen gas making water. So I want to draw it. I have a hydrogen, no, color that in, a hydrogen gas, and then I have an oxygen gas. Do you already have these pictures in yours?
Yes.
Okay, and then I have a water. Now notice how many of things I got. I have 2 hydrogen atoms, 2 hydrogen atoms. That's all right. 2 oxygens, only 1 oxygen. I'm disobeying the law of conservation because where'd that oxygen go? Oxygen cannot be created or destroyed. It can only change from one form to another. So what I have to do is balance it. And how I'm going to do it is I'm going to go back and add another water. Now I've got 2 waters. That takes care of my 2 oxygens. But now I have 4 hydrogens. So I need another molecule of hydrogen. So this means I have 2 hydrogens, 1 oxygen, and 2 waters. The numbers in front tell how much. The little numbers, the subscripts tell you the atoms in the molecule. The numbers in front can be changed. The little numbers can never be changed because then you're changing the compound. If I had just gone in and put a little 2 down there, then it wouldn't be water anymore. It'd be hydrogen peroxide. Hydrogen peroxide would kill you to drink it. And the kind you buy, the kind we used in lab in the brown bottles, is only 3%. You can drink a little of that and not die. People will use it and swish their mouth out if they have ulcers in their mouth, and they don't die. You know, they might swallow a tiny amount, they don't die. 30% strips your hair and bleaches it. So can you imagine what drinking 100% peroxide would do to you? It would kill you. 30% would kill you.
You know, it makes your digestive tract smaller.
Yeah, that's true. It'd mess you up. All right. So you do not change subscripts. That's changing the chemical. That's the little number at the bottom. Do not change subscripts because that would change the chemical. Do change the coefficients, the big numbers out front. Did everybody learn how to do this in 8th grade?
Yeah.
Good. All right, well, today's a good day to learn it. Never insert a number between the elements in the same molecule. All right, so we are going to balance some chemical equations. Okay, so how we do this? Now, there are different ways different teachers teach this. Some teachers teach you to draw a little chart underneath. That's baby. Y'all are real scientists. Y'all are honors kids. We're not going to draw any charts. How we're going to do it is just like how I taught you to use the periodic table to figure out electron configurations and not use the chart because it's faster and better. Same thing with this. We're not going to use any charts. We're just going to go back and forth till it's right. So you need to do this in pencil. When I do one of these, I always make sure that the reaction is written in pen if I have to handwrite the reaction, and I balance it in pencil because you're going to have to erase. Got it? All right, so on this side, how many silvers do I have? 1. How many do I have over here? 2. So I go over here and I write a 2. And then I keep checking everything. How many hydrogens do I have?
2.
How many do I have?
2.
How many sulfurs?
1.
How many sulfurs?
1.
It's all balanced now. Now, sometimes I will be tricky, and I'll give you one that's already balanced, just to make it harder. So don't let that throw you. Another thing is, well, I'll show it to you in a minute. Okay, so let's try this one. How many phosphorus do I have over here? How many do I have over here? 2. Now, it looks like I would maybe just put a 2 here. But let me also tell you, different teachers have different opinions about this too. I like to do oxygen last. I go back and forth and do oxygen last. Don't write this until I tell you that we're done. Just watch me do it. Okay, so 4, over here I have 2. Okay, now I have one potassium, one chlorine, everything looks pretty good, but my oxygen is 2 times 5, which is 10 over here, and over here it's 3. Is there anything we can multiply 3 by to get 10?
No.
No. So I'm gonna have to go back and erase. Come on, eraser. Come on, eraser. Eraser. Ah! So
You're the select right now. Oh.
okay, yay. Now we can try again. Okay, so we're on, we did that one, it added 2. And now we're on this one, and it got rid of it. Okay, so now I'm going to instead think about, remember middle school math, least common multiple, greatest common factor, or GCF, or LCM as the cool kids would call it. Remember that part of middle school math? Well, we actually use this here, because we're going to say, what is the lowest number that 5 and 3 both go into? They both go into 15, right? So we're going to try that one next to see how that works. So I'm going to put a 3 here and a 5 here. So now these are balanced. But now I got to look back at my phosphoruses. Phosphorus is 2 times 3, which is 6. Is there anything I can multiply 4 by to get 6? No. So this one's a really tough one. Most of them won't be this tough, but I give honors a few tough ones. I want y'all to take just a second and see if you can figure it out. Everybody just own your own, see if you can figure it out. You know it didn't work with doing the odds over here with the oxygens first. It didn't work with doing the evens with the phosphorus first. So we're going to have to find something that works for both of them. We're going to have to go bigger. We're going to have to go bigger. I'm going to try erase again. I know I'm being a little crazy here trying to erase. Oh, look, I'm erasing. Did anybody get it yet? Anybody want to see if you got it? Jeffrey? You think you got it?
Yeah, a couple seconds because I got the numbers, but I think I know what I need. Yeah.
You think you know what you need? So think back to our least common multiple. 15 didn't work. So remember middle school? If 15 doesn't work, what do you go to? 30. There's your clue. Did that help?
Yep.
Yep. You got it? I did it. Did y'all get it? 3, 10, 10, 6. So now I've got 3 times 4, which is 12 phosphorus. 6 times 2 is 12 phosphorus. 6 times 5, which is 30 oxygens. 10 times 3, which is 30 oxygens. 10 times 1 is 10 potassiums and chlorides. 10 times 1 is 10 potassiums and chlorides. Did anybody figure that out then with that help? So a couple of things here. Don't be afraid to go big. Sometimes you have to go big. All right, let's try the next one. See if you can do this one by yourself. NaCl, NaCl. This one's easier. See if you can do it. Give it a try. So you've got 1 sodium over here, 1 sodium over here. They're fine. 2 chlorines over here, 1 chlorine over here. So what do I need? A 2. Now I have to go back. 2 sodiums over here. What do I need over here? A 2. Is this starting to make sense? Is this going to be easier than the last unit? Okay. All right, so let's try this one. 6 carbons, 1 carbon. So what do I need over here? a 6. 12 hydrogens over here, 2 over here, so what do I need? A 6, because 6 times 2 is 12. Now I have 6 oxygens plus 12 oxygens is 18, and I have 6, so, and here I have 2 oxygens, so what do I need to multiply this by so that the whole thing will be 18? 6, somebody said it. So 6 times 2 is 12 plus 6 is 18. You do the math here. So if the oxygens are split or whatever it is, and then there's that plus there, you have to plus. Does that one make sense to you? A little bit trickier. You're going to get to practice this so much, you're going to be great at it. Last year I gave them like 10 pages of these to practice. Okay, let's try another one. Okay, so C2, O2, CO2, H2O. Okay, over here I have 2 carbons. What do I have over here? I've got 1, so what do I need? A 2. I've got 1 hydrogen here and 2 here, so what do I need there?
2.
A 2. So that messed up. So now I need to go back and change this one to what? 4. I'm going to just mark it out instead of trying to erase it. So now that one's 4. Now let's look at our oxygens. I have 4 times 2, which is 8, plus 1 is 9. Does this one make sense? This one's real important. Pay attention to it. It's a little bit different. Over here I have 2. What can I multiply by 2 to get 9? Nothing. But if I could, you can't split atoms. That causes bombs and death and destruction and stuff like that. But if I wasn't, not really splitting atoms, but splitting molecules here, if I could do it, if I could use a fraction, what do you multiply by 2 to get 9? 4.5. Now, you're not allowed to have fractions. But if you can balance it with fractions, go ahead and do it, and then multiply it by the denominator, and you'll have the right answer. I call it the amazing doubling rule, because usually you double it. Sometimes the fraction is a third, and then it's the amazing tripling rule. But this is the amazing doubling rule. This will get you out of so many jams. You cannot believe it. So all I have to do is go back, and this one will be 4. This one will be 9. That one will be 8. And this one is 2. There's an understood 1 there. So don't forget to double that one also. How do we feel about that? All right? Oh, Lael said, no, this is awful. All right, I'm leaving those 2 easy ones for y'all to do on your own. Do you have it on your paper, those 2? No? Well, then you'll have a worksheet with it. What? We only have 4 minutes of class left. That's so sad. All right, let's see how far we can go. What information is an equation? Equations are instructions. So just like in your recipe, you're going to have a temperature to cook it at. You're going to have a time, how long to cook it, right? Equations also tell us a little bit about those instructions. Let's see. We could do one little bit more.
That's 3 minutes.
I know, 3 minutes. And there's a good chance it's not going to scroll. But it did scroll. All right, we already got this. Sometimes the energy will be written in the equation. If it's written in the products, it's exothermic. If it's written in the reactants, it's endothermic. Also, sometimes it's written at the bottom, and it's the change in heat is the energy. And if it's endo, it is negative, and if it's exo, it is positive. So sometimes they just write at the bottom. Reactions also will sometimes tell you the state of matter, if it's solid, liquid, or gas. And we'll stop there and pick it up tomorrow. So part 2, come back. Science is great. Like, share, subscribe. It's not stopping. Ah!